Hello, friends. There has been a really disturbing development earlier this month, particularly for those of us on the carnivore diet. The big food, big pharma corporations have crafted another deeply sinister plot, perhaps the biggest so far, with severe consequences related to the health and well-being of us all. It is really hard to believe, but now that the buzz has settled down a bit after the announcement of the Nobel Prize winners for this year, the dark truth and the bitter reality associated with these awards is slowly coming to the light. Especially after what we have found out about the prize given in the field of chemistry, a lot of pinching questions have come out. Like it or not, the research and developments related to the design and prediction of new protein structures, which have culminated and manifested in the form of this prestigious most award, are not so angelic as they are shown to be. We have no disrespect towards the researchers or their efforts put into their work, but the thing is, this has far more consequences apart from the apparent benefits being told to us. And for the ease of our viewers, we are going to explain how this whole thing is going to have a deep impact on the lives of us all, particularly those of us striving to cure and heal various chronic conditions through proper human diet and nutrition, with the carnivore diet being the prime most example of this lifestyle. So, what really is bad about this year's Nobel Prize, and how it is going to literally destroy our nutrition in the days to come? Let's have a look. Well, friends, in a landmark development, the 2024 Nobel Prize in Chemistry has been awarded to David Baker from the University of Washington and Demis Hassabis with John Jumper from Google DeepMind, marking a transformative moment in the field of molecular biology. According to the Nobel Prize Committee, their work addresses two long-lasting critical challenges: the design of new proteins and the prediction of natural protein structures. David Baker, recognized for his achievements in computational protein design, has spent years perfecting methods to build proteins from scratch, proteins that do not exist in nature but can be crafted to perform highly specialized tasks. The other half of the prize acknowledges the work of Hassabis and Jumper, who developed AlphaFold 2, an artificial intelligence model that solved the decades-long problem of protein folding. The folding pattern dictates a protein's function, and predicting these structures accurately was considered one of biology's most difficult problems. In rather simple terms, proteins, which are the essential molecular machinery of our life and an integral component of the carnivore diet, govern nearly every biological function, from enzyme catalysis to immune responses. And these breakthroughs actually redefine how we understand and manipulate life's fundamental molecules, with implications that extend well beyond our imaginations. The potential applications, including medicine, biotechnology, and more importantly, food science, are so staggering that we really need to know how this enormous power will be wielded by the big corporations and what untold consequences it would bring to us all. As we move deep into this exclusive video, we'll untangle all these crucial questions in a proper scientific manner, all based on accurate facts with logical reasoning. The stakes are really high for us, and the answers are not as straightforward as they may seem to be. So watch with all your attention and concentration, as none of this vital info is available anywhere else on YouTube. The real story is about to begin. Friends, before revealing the true motive of big food and big pharma related to these award-winning developments, it is important for us to first understand the real purpose and science behind these research initiatives. Let's begin with decoding the Nobel Prize, what really was the problem at hand, and what eventually came out. As we all know, proteins are the essential molecules in our body that carry out virtually all biological functions, facilitating metabolism, immune response, energy production, and cell communication. However, understanding and manipulating these complex structures has remained one of the most difficult challenges in molecular biology. A protein's function is dictated entirely by how it folds into a precise three-dimensional shape, but predicting this shape from its amino acid sequence has eluded scientists for decades. This difficulty is known as the protein folding problem, first formulated in the 1970s. Despite advances in experimental techniques such as X-ray crystallography and nuclear magnetic resonance spectroscopy, solving the structure of proteins remained a slow and resource-heavy process. Each protein required dedicated work that could take months or years, thus hampering scientific progress, particularly in areas like medicine discovery and enzyme engineering. Alongside the challenge of understanding natural protein structures, researchers also faced the limitation of biological evolution. Natural proteins are the result of millions of years of evolutionary fine-tuning, optimized for the survival needs of specific organisms. However, the functions needed for modern medical and industrial purposes often require new types of proteins, molecules that do not exist in nature. Designing these proteins from scratch presented enormous technical hurdles. Without the ability to accurately predict how sequences would fold, it was difficult to create proteins with desired functions. This dual challenge, predicting protein structures and designing functional proteins, represented a major bottleneck for biotechnology, medicine, and other scientific branches. In response to these challenges, scientists pursued two parallel paths: improving protein design algorithms to create new proteins from scratch, and developing predictive tools to unlock the structures of natural proteins faster and with greater precision. These efforts culminated in the breakthroughs that earned the 2024 Nobel Prize in Chemistry. Now, the obvious question that comes to mind is that how are these magnificent scientific developments a threat to the carnivore diet, or in simpler terms, the proper human diet and nutrition? Well, we certainly are going to describe this, but for that, we need to know these details discussed ahead. Solving the almost impossible design problem with computational protein engineering. Well, friends, Dr. David Baker's controversial yet groundbreaking work addresses the challenge of de novo protein design, the ability to create new proteins from scratch for specific applications. His lab developed Rosetta, a pioneering computational platform that simulates how amino acid sequences fold into stable, functional structures. This tool has evolved over the past 2 decades into one of the most powerful resources for protein engineering, allowing researchers to bypass the limitations of natural proteins and create entirely new molecules. Baker's team demonstrated that proteins could be designed to carry out highly specialized tasks, such as functioning as enzymes that break down environmental pollutants or molecular sensors capable of detecting disease markers. A particularly noteworthy achievement is the creation of a synthetic medicine for respiratory syncytial virus, RSV, the first de novo designed medication to enter clinical trials. This development highlights the transformative potential of custom protein design in the field of medicine, paving the way for more effective and precise therapeutics. Beyond medicine, Baker's designs extend into fields like nanotechnology and green chemistry. His lab has produced enzymes that can break down plastics and materials with enhanced properties for use in industry. The power of computational design lies in its ability to solve problems faster and more accurately than traditional trial-and-error methods, reducing reliance on natural proteins and expanding the toolkit available to scientists and engineers. Moving to the other half, solving the protein folding problem with AlphaFold 2. While Baker tackled the design problem, Demis Hassabis and John Jumper of Google DeepMind confronted the protein folding problem, a puzzle that had frustrated biologists for over 50 years. AlphaFold 2, their deep learning-based AI model, achieved what many believed was impossible, accurately predicting the 3-dimensional structure of proteins directly from their amino acid sequences. This feat was made possible through neural networks trained on large datasets of protein sequences and structures, combined with advanced optimization techniques to generate predictions with atomic-level accuracy. According to the developers, AlphaFold 2's impact has been really profound. Since its release in 2020, the system has solved the structures of more than 200 million proteins, providing researchers with insights that would have taken decades to uncover using experimental methods. Scientists have used AlphaFold 2 to study antibiotic resistance mechanisms, model viral proteins, and develop new enzymes for industrial applications. Its open-access model has democratized protein research, making these insights available to millions of researchers worldwide across 190 countries. The predictive power of AlphaFold 2 has revolutionized several scientific fields. In medicine, it accelerates medication discovery by revealing the exact structure of target proteins, allowing for the design of more effective medications. In materials science, it enables the development of custom enzymes for sustainable chemical processes. By solving the protein folding problem, Hassabis and Jumper have provided a tool that streamlines research and innovation across numerous disciplines. Together, the work of Baker and the DeepMind team represents a paradigm shift in molecular biology. With the ability to design new proteins from scratch, and predict the structures of natural proteins with precision, scientists apparently now have tools that dramatically expand the frontiers of biotechnology. These breakthroughs promise to revolutionize medicine development, industrial bioprocesses, and environmental science by providing faster, more effective solutions to previously intractable problems. However, as these technologies mature, they raise new unanswered questions. Although the custom-designed proteins and AI-predicted structures offer incredible potential, but they also pose a risk to our biological system, taking it to the level of man versus nature. So, how will these new proteins behave over time? What are the unforeseen risks associated with engineering molecules that do not exist in nature? And most importantly for us, how these artificial new proteins are going to affect our dietary health and nutrition. As we unfold the details further, this is where it gets crucial for us all, following the diet plans with proteins as an integral part of the whole picture. But before revealing the adverse impact of these developments on our food and nutrition, let's have a brief look at some other associated aspects and benefits of the award-winning research. Transforming medicine, precision therapies with engineered proteins. Friends, according to the researchers, medicine is one of the primary fields poised to benefit from these breakthroughs. Traditional treatments often rely on broad-spectrum pharmaceuticals that impact healthy and diseased cells alike, leading to side effects and reduced efficacy. With the ability to design targeted protein-based therapies, researchers can now develop precision treatments that interact only with specific biological pathways, minimizing unintended effects and improving outcomes. For example, synthetic antibodies, proteins engineered to bind precisely to disease-related molecules, offer promising new approaches to treating cancers and autoimmune disorders. David Baker's lab has also developed customized immune activators designed to trigger precise immune responses against specific pathogens, including an experimental therapy for respiratory syncytial virus, RSV. These tailored protein treatments are unencumbered by evolutionary constraints, marking the dawn of a new class of highly specialized medical interventions. Plus, AlphaFold 2's predictive capabilities have accelerated the development of therapies by providing accurate models of disease-relevant proteins. This insight enables researchers to identify new therapeutic targets more rapidly, especially in cases where conventional methods would take years. A prominent application involves modeling antibiotic resistance proteins, helping scientists develop new treatments that overcome bacterial resistance, which is one of the most urgent challenges in modern healthcare. Next, revolutionizing industry, green chemistry, and environmental solutions. Friends, the implications of these breakthroughs extend beyond healthcare, reshaping industrial biotechnology and green chemistry. Enzymes, which catalyze essential chemical reactions, play a crucial role in numerous industries. However, natural enzymes often come with limitations in efficiency and stability. Baker's work on synthetic enzymes eliminates these constraints, enabling the creation of highly efficient catalysts tailored for specific industrial processes. Apparently, one of the most promising applications is the development of enzymes capable of degrading plastics, offering a potential solution to the global plastic waste crisis. These custom-designed proteins can break down plastic molecules at a molecular level, creating opportunities for sustainable recycling systems. Additionally, synthetic enzymes are being employed in biofuel production, enhancing the efficiency of converting biomass into fuel and accelerating the transition toward renewable energy sources. AlphaFold 2 has also facilitated the optimization of industrial enzymes by providing precise models of their structures. This insight allows companies to fine-tune catalysts for pharmaceutical manufacturing, agriculture, and other fields, improving efficiency while minimizing environmental impact. The result is a new generation of sustainable industrial processes that rely less on harmful chemicals and more on biological catalysts tailored for green chemistry. Next up, we will explore how these developments are beginning to severely influence the food science and nutrition. What are the top health risks associated, particularly for those of us following high-fat, high-protein diet plans like keto and carnivore, where the tension between natural and synthetic solutions is already becoming increasingly significant? But before moving ahead, we would like to know which diet plan you are currently following: carnivore, keto, or some other. And what health conditions have you healed so far? Do share your experience in the comments. The severe food and nutrition implications. Well, friends, the 2024 Nobel Prize in Chemistry, awarded for advancements in new protein design, marks a pivotal moment in science, allowing scientists to precisely design proteins with unprecedented accuracy, reshaping fields from medicine to food science. While this achievement has a mighty transformative potential, it also opens the door to unsettling developments related to synthetic food production. Companies, notably Upside Foods and Savor, both backed by Bill Gates, are applying these innovations to create lab-grown meat and artificial butter. Though these projects are marketed as sustainable solutions to reduce environmental impact, they also present a hidden danger: the gradual elimination of natural animal-based foods from our diets. This shift risks depriving people of the essential nutrients found in real meat and butter, critical elements for high-fat, high-protein diets such as the carnivore diet, which many individuals follow to optimize health and wellness. While the scientific world celebrates the creation of synthetic proteins, these technologies are aimed to ultimately drive consumers away from nutrient-rich natural foods. Lab-grown meat and artificial fats are touted as replacements for red meat and animal butter, but in reality, they are nutritionally far inferior and could lead to severe long-term health consequences. A deeper examination of how these synthetic products are made and how they compare to their natural counterparts reveals significant cause for concern. Lab-grown meat, a poor substitute for nutrient-dense red meat. The concept of lab-grown meat originated from research in tissue engineering, aiming to replicate animal muscle tissue outside of the body. The process begins by extracting stem cells, or muscle precursor cells, from a living animal. These cells are placed in a nutrient-rich culture medium, where they multiply and form muscle fibers. The medium typically contains a blend of amino acids, glucose, minerals, vitamins, and growth factors. Early versions of this technology required fetal bovine serum, FBS, a substance derived from the blood of unborn calves, to stimulate cell growth, although companies are now working to replace FBS with plant-based alternatives. In bioreactors, the muscle cells are exposed to hormonal and chemical signals that trigger them to differentiate into muscle fibers. These fibers are grown on scaffolds to mimic the texture of natural meat. However, the final product is essentially a collection of cells without the complex network of tissues, connective elements, and fats that give real red meat its unique nutritional profile. Natural red meat, particularly beef, lamb, and organ meats, contains a wealth of essential nutrients that lab-grown meat cannot replicate. These include heme iron, which is highly bioavailable and critical for preventing iron deficiency, vitamin B12, vital for brain and nerve function, and omega-3 fatty acids, which play a role in cardiovascular health. Red meat also provides a complete profile of essential amino acids, creatine, and carnitine, which are necessary for muscle function and energy metabolism. In contrast, lab-grown meat lacks many of these nutrients or provides them in forms that may not be as bioavailable. While synthetic meat can offer protein, it may fall short in essential micronutrients such as zinc, selenium, and fat-soluble vitamins, A, D, E, and K, that are found abundantly in natural animal meat. Additionally, the long-term effects of consuming lab-grown meat remain largely untested. Some experts express concern that this engineered product could alter gut microbiota, increasing the risk of metabolic and immune disorders over time. Consumers drawn to lab-grown meat for its environmental promise may unknowingly sacrifice their health. The carnivore diet, which relies heavily on nutrient-dense animal products, demonstrates the profound benefits of a high-fat, high-protein diet. Many followers report improvements in metabolic health, mental clarity, and reduced inflammation. Replacing these whole foods with synthetic alternatives poses a direct threat to those seeking optimal health through natural nutrition. Similar to the synthetic meat, artificial butter from air, a nutritional and chemical mirage. In a parallel effort to replace traditional animal fats, companies such as Savor, also backed by Bill Gates, are developing artificial butter using carbon capture technologies. This innovative process involves transforming carbon dioxide, CO2, hydrogen, and oxygen into synthetic fats through a combination of thermochemical reactions. While this process might sound like a scientific marvel, it raises serious concerns about nutritional adequacy and long-term health risks. Natural animal butter, derived from milk, contains far more than just fat. It is a rich source of conjugated linoleic acid, CLA, a unique fatty acid with proven anti-inflammatory properties and potential benefits for fat loss. Butter also contains essential fat-soluble vitamins, such as vitamin A, which supports vision and immune function, vitamin D, crucial for calcium absorption and bone health, and vitamin K2, which plays a role in cardiovascular health by preventing arterial calcification. These nutrients exist in perfect synergy within natural butter, promoting efficient absorption and optimal health. In contrast, artificial butter lacks these complex nutritional benefits. While it may replicate the taste and texture of real butter, it offers little more than empty calories. The synthetic fats produced from carbon capture are stripped of the essential bioactive compounds found in natural animal fats. Furthermore, the long-term effects of consuming chemically engineered fats are unknown. The introduction of such products into the food supply could alter cholesterol metabolism, hormone regulation, and immune responses, leading to unforeseen health complications in the years to come. Replacing natural butter with a synthetic alternative also undermines the principles of nutritional freedom and dietary autonomy. Diets that emphasize animal-based fats, such as the carnivore diet and ketogenic diet, have shown profound health benefits, including improved insulin sensitivity, cognitive function, and cardiovascular health. Artificial butter, however, offers no comparable benefits and represents a step backward in nutritional quality. To put it simple, the movement toward lab-grown meat and artificial fats is accelerating, with venture capital giants and high-profile investors like Bill Gates pushing the development of these products. While such developments could reduce the carbon footprint of livestock agriculture, they introduce some profound questions for our health and wellness, which are eventually the game changer. And finally, moving to the most important section of the video, we are going to reveal the major health risks associated with the consumption of synthetic proteins and fats. The mighty health risks. Well, friends, the risks posed by synthetic foods, especially those derived from engineered proteins and fats, extend far beyond the superficial concerns of novelty. While these innovations are marketed under the promise of sustainability and progress, they carry serious health risks that remain largely untested. As synthetic alternatives begin to replace traditional sources of nutrition, the long-term impact on human health and biological well-being raises urgent and critical questions. Relying on lab-grown foods and artificial proteins threatens to disrupt metabolic balance, immune function, and nutrient absorption in ways that could cause profound, irreversible damage over time. One of the most immediate concerns revolves around the issue of nutrient bioavailability, the extent to which nutrients are absorbed and utilized by the body. Natural animal products, such as meat, fish, and dairy, provide essential nutrients in bioavailable forms, including heme iron, vitamin B12, long-chain omega-3 fatty acids, and complete amino acid profiles. These nutrients play irreplaceable roles in cellular metabolism, brain function, and immune health. Attempts to replicate these profiles in lab-grown meat or artificial butter face significant limitations. Even if the chemical structure of synthetic proteins mimics that of their natural counterparts, the complex synergies between nutrients present in real foods are exceedingly difficult to replicate in artificial systems. Replacing real animal-based proteins with synthetic ones risks introducing metabolic inefficiencies. The human digestive system has evolved over millennia to process and absorb nutrients from natural foods with remarkable efficiency. Introducing synthetic proteins or lab-grown alternatives could disrupt gut microbiota, the complex ecosystem of microorganisms essential for digestion, immunity, and hormonal balance. Disruptions to this microbiota have been linked to autoimmune disorders, metabolic syndromes, and chronic inflammation, conditions already on the rise in modern societies. Long-term reliance on artificial foods without fully understanding their effects on gut health could exacerbate these conditions and create new, unpredictable health risks. The long-term health impact of consuming synthetic fats is another area of serious concern. Fats derived from carbon capture processes, such as the artificial butter developed by Savor, may replicate the taste and texture of natural fats, but there is no comprehensive understanding of their metabolic behavior. Natural fats, particularly those from animal sources, contain bioactive compounds like CLA, conjugated linoleic acid, and phospholipids that support heart health, immune function, and brain development. Synthetic fats are unlikely to carry these same benefits, and consuming them as a substitute for natural fats could disrupt lipid metabolism, increase the risk of inflammatory diseases, and impair brain function over time. The commercialization of synthetic proteins also presents a monopolization risk. If key technologies, such as those used in precision fermentation and cultivated meat production, remain under corporate control, it could limit public access to nutrient-dense natural foods, consolidating power within a small group of companies. This monopolization of food systems raises the possibility that decisions about what we eat will be dictated by profit motives rather than health priorities, further undermining our individual autonomy and dietary freedom. Friends, in simple words, the 2024 Nobel Prize in Chemistry recognizes a monumental achievement in protein design, but the practical application of this technology in synthetic foods raises serious concerns. The widespread adoption of lab-grown meat and artificial butter threatens to displace natural animal products from the food system, depriving consumers of essential nutrients that are critical for health and longevity. This shift also risks eroding cultural and dietary diversity, as many cuisines rely heavily on real meat and animal fats. The environmental narrative surrounding synthetic foods may obscure the hidden costs to human health. Governments and corporations, incentivized by sustainability goals, could push lab-grown alternatives through regulatory frameworks and economic pressure, making real meat and butter harder to access. If these trends continue, future generations may find themselves trapped in a food system dominated by engineered products with inferior nutritional value. As exciting as the advances in protein design may be, blindly adopting synthetic foods without considering their long-term health implications would be a grave mistake. Nutritional science tells us that whole, natural foods provide irreplaceable benefits that cannot be replicated in a lab. To preserve health, wellness, and dietary freedom, it is essential to push back against the marginalization of real foods and demand transparency in how new technologies are applied in the food industry. By the way, what is your opinion on this whole development? Would you try any synthetic food in your diet? And how has your experience been on the carnivore diet? What health conditions have you healed so far? Do share your journey in the comments. Press the like button if you found this video helpful, and share it with your loved ones as well. Subscribe now to our channel to get more of such highly informative content about your health and well-being. And if you want to know what special happened 100 years ago related to keto and carnivore, click on the video showing up on the screen to find that out. See you there.